This is Valarmati, Assistant Professor working in RMK Engineering College. This session contains the topic exponential distribution. First we see the contents. First is definition of exponential distribution, then how to derive MGF, mean and variance. Third is memoryless property, diagrammatic explanation is also given. Then last is example to understand this memoryless property better. Now we go to the session. First is definition. It is a continuous random variable x defined in the interval 0, infinity is said to follow an exponential distribution if the probability density function is defined as f of x equal to lambda into e power minus lambda x, where lambda is a parameter, x takes the values between 0 to infinity. This f of x is equal to lambda into e power minus lambda x is the formula for exponential distribution. Now using this formula we derive moment generating function, mean and variance. First, moment generating function, the notation is mx of t, which is equal to e of e power tx, that is equal to integral 0 to infinity e power tx f of x into dx. This is a formula for moment generating function. Now in the place of f of x we substitute lambda into e power minus lambda x, then integrate. Before that take the lambda outside, because it is a constant we take it outside. Now combine this e power tx into e power minus lambda x, bases are same, so you can add the powers, we get e power minus of lambda minus t of x into dx. We integrate this, so we get the answer lambda into e power minus of lambda minus t into x divided by minus of lambda minus t. Limits are 0 to infinity. First substituting upper limit we get 0 and lower limit we get numerator is 1. So minus of minus, the answer is lambda by lambda minus t. This is called moment generating function value. Now we see that how we are going to find mean using this moment generating function. For this, first what we do, we find the first order differentiation of mx of t, which is nothing but lambda by lambda minus t whole square. Differentiation of mx of t at t equal to 0 is denoted by mu 1 dash, and now the value is lambda by lambda minus 0, that is in the place of t you substitute 0, you get lambda by lambda square. If you cancel that, the answer is 1 by lambda. Now similarly second order, find the second order differentiation of mx of t, that is equal to 2 lambda by lambda minus t whole cube. Now similarly as we substitute t equal to 0 in before equation, like that here also I am substituting t equal to 0, which is denoted by mu 2 dash, that is equal to 2 lambda by lambda minus 0 whole cube. If you simplify this we get the answer 2 by lambda square. Now mean is nothing but mu 1 dash, the answer already we found, that is 1 by lambda. Now we see how to find this variance. Variance formula is mu 2 dash minus mu 1 dash whole square. We got the values already, just substitute, that is equal to 2 by lambda square minus 1 by lambda whole square. If you simplify this, this is equal to 1 by lambda square. Therefore mean is 1 by lambda, variance is 1 by lambda square. Okay, now we go to the next session, that is memoryless property of exponential distribution. We see the statement, if x is exponentially distributed with parameter lambda, then for any two positive integers s and t, probability of x greater than s plus t given x is greater than s, which is equal to probability of x is greater than t. Now, we see the proof. To prove this, first we define what is this f of x. Using exponential distribution definition, we are writing this PDF of x is f of x equal to lambda e power minus lambda x. Now, we are going to define what is this probability of x greater than k. For example, instead of t or s, I am choosing this k first. So, x greater than k means after this k we have to take all the values, that is lower limit is k, upper limit is infinity into f of x dx. This is a formula. Now, in the place of f of x, substitute this lambda into e power minus lambda x. Take the lambda outside and integrate e power minus lambda x. We get the answer e power minus lambda x by minus lambda. Substituting upper limit and lower limit, we get the answer e power minus lambda k. We consider this as equation 1. Now, we continue this, that is already it is given in the statement s and t are two positive integers. That means we have to take the positive values only. So, in this case I am taking LHS equal to RHS. This is one type of proof. We can prove LHS equal to RHS also. So, now I am choosing what is LHS? Probability of x greater than s plus t, condition x is greater than s, which is equal to, how we are writing this value means p by a, probability of a by b, which is equal to probability of a intersection b divided by probability of b. So, using this formula, we write this as probability of x greater than s plus t intersection x is greater than s divided by probability of x greater than s. To find this intersection value, we consider an x axis. So, already it is given, we have to choose only the positive values. So, I am taking first 0 and then next point is s and then another point is t and the last point is infinity. Now, this area is called it as greater than s area and this area is called it as greater than t area, which is also call it as s plus t because this place contains both s and t. Now, what is the intersection value now? Probability of x greater than s plus t alone we get it divided by probability of a x is greater than s. Now, using equation 1, what is the value? If you are having probability of x greater than k means we can write that value as e power minus lambda k. Similarly, here e power minus lambda of s plus t divided by e power minus lambda s. If you are cancelling this e power minus lambda s, we get only e power minus lambda t. Now, which is nothing but probability of x greater than t. So, we proved that LHS equal to RHS, that is probability of x greater than s plus t given x is greater than s means we get only probability of greater than t. To understand this better, I consider one example. Now, see what is the example? Suppose that during a rainy season in a tropical island, the length of the shower has an exponential distribution with average 2 minutes. If the shower has already lasted for 2 minutes. Now, what is the question means? What is the probability that it will last for at least 1 more minute? So, what is the question? Already it is showered for last 2 minutes. Now, including that with 1 more minute. So, we have to find this. First we consider what is given. X is a random variable which follows exponential distribution. That means we are considering exponential definition here. So, first what is this average? Average is nothing but mean. Mean of exponential distribution is 1 by lambda. So, we need only lambda, that is 1 by 2. Now, we know what is the definition. F of x equal to lambda into e power minus lambda x is the exponential distribution value, which is equal to, in the place of lambda you substitute 1 by 2, we get 1 by 2 e power minus x by 2. Actually, what we have to find, probability of the shower will last at least 1 more minute, given that it has lasted 2 minutes. Totally we have to find for 3 minutes, that is s plus t. Here we are using this probability of x greater than 3 condition. Already it is showered for 2 minutes, but instead of finding for this whole value, now I am going to reduce this as 2 plus 1 and it is like s plus t. Okay, now using the memoryless property, instead of finding for all these 3 minutes, I am going to find only 1 minute. They are equal using this property. So, start with the lower limit 1 to infinity 1 by 2 e power minus x by 2 into dx. So, now take this 1 by 2 outside, integrate e power minus x by 2, we get the answer 1 by 2 into e power minus x by 2 divided by minus 1 by 2. So, lower limit is 1, upper limit is infinity. So, we get the answer, final answer is e power minus 1 by 2, because e power minus infinity value is 0 and in between minus is there, before also our minus is there, minus into minus become plus. So, we get only the answer e power minus 1 by 2, that value is 0.6065. Next session we will see the next one more distribution. Now, thank you.